Okay, so now let's move to an inelastic collision example. So remember the definition, what does that mean? That means kinetic energy is no longer conserved, okay? So momentum is conserved as long as in the whole system, there's no net force on it, okay? So this is the example. We'll do the same strategy of drawing a before and after. And we'll have a railway car hitting another one. Let's say each of them, again, have the same mass, but you can solve if they are different. But I will solve MA equals to MB. Okay, let's say it's 10,000 kilograms. Okay, something like that. Let's say 10 tons or something like that. Right. So this guy is moving, let's say at 55 miles per hour, and hit something that is standing still. All right. Let's give it labels. So this is going to be UA is 55 miles per hour. Notice this time I am writing a unit because it's miles per hour. It's not a standard SI unit. So I'll need to specify it here. Otherwise, if I don't, I might mistakenly just plug this in my equation without writing the unit, and that's where trouble exists, right? So, but what I will do very shortly, I'll just, because I decided to include this as well, so to show you if the problem did not give you an SI base units, how are you going to deal with it? So this is my strategy of doing it, right? Write it down here, and as soon as I finish drawing my diagrams, I'm going to convert this to SI units, and at start of SI, I have no need to worry about what it is until what the unit is until at the end, right? And you'll be again at rest, okay? And also I'll try to write everything in terms of symbols, in terms of variables, and not plugging values anyway. But yeah, afterwards, this time they are coupled together. So you will the question will tell you that if something is coupled together, they should tell you explicitly whether it's elastic or inelastic. If they didn't say it's elastic, you might want to consider if it's inelastic. But just a general rule, when something sticks together or when something splits, instead of like before, when the billiard ball, they don't stick together, right? Or after the collision, the two things are still individual items. They did not split into three things, or they're not combined into one thing, right? Two things stays two things. But here, two things combine into one collective object, and they're going to move together. Just thinking of momentum conservation, right? So this would move this way. It's impossible after they stick together, they'll move this way. It just doesn't make sense. So I'm going to define my positive V this way anyway. Should I put VA or VB? It doesn't matter. In fact, it's a V collective. So if you want, it's VA plus B, like that, okay? But I'll just use V because otherwise there's too much to write. So lazy means we can just do this. So question mark, that's what I want to solve. And what's the mass over here? Well, the mass is obviously MA plus MB. But in case I need to use it, I'm going to let capital M equals MA plus MB. Okay, I might not need to use it, but just in case. So just showing you general strategy of solving problem. Now, in some sense, in elastic problems, you might think it's more difficult because there's friction, there's coupling, right? There's extra forces going on. But now you just have to ask yourself, as the whole system, is there extra force on it? Is there external force to the system? Now, there is a force to sort of pull them together, to couple them together. There's a contact force somewhere, some tension, some normal force, some tension going on. But those are all internal forces, not external, right? It's not external from the system. So conservation of momentum applies. Okay, so we can write down that, but we don't write down conservation of energy because energy is conserved, but kinetic energy is not conserved. Part of that went to the force of coupling them together, the energy of just holding them together. And part of it went to friction and heat and etc. Okay, so we're not going, in some sense, inelastic collision problems are easier because you only have one equation to work with. You don't have two. Okay, so we'll see how this works, right? So you start off, what's the initial, the total momentum initially? Well, MA, sorry, yeah, let me write one more step. So P initial must equals to P final if I add all of them up. So initially I have PA plus PB initial. And afterwards, I just have, let's say, capital P, right? PA plus B. final, like this. Okay, so now we're going to plug in the momentum for A and momentum for B initially. So it's MAUA plus MBUB. Now I could have just plugged in UB equals 0, but I'll solve it generally first. So just to get you used to working with variables, and I recommend doing that for all the problems, collision problems as well. Try to work with variables as much as possible, just to get your practice, right? And here, what's the final momentum? Well, it's the combined mass times V, right? So I can use capital M and V. That's it. That's the total momentum, okay? What is my goal? My goal is to solve for this. That's the unknown, right? What is known? I know MA, right? I know MB, I know UA, I know UB. And do I know capital M? Yeah, that's just my shorthand, right? So that's why it's important that I label this in case I use it. And this is one equation, one unknown. So you see, inelastic problems are actually almost easier, all right? So we can do that, right? So to find V, right? Then this is, yeah, so this is basically MAUA plus MBUB divided by, I'll expand this out, MA plus MB, and it's done. Okay, now I just need to plug in the numbers. So I'll plug in, let's see, this is the general formula of what happens when they couple together. And I will plug in the numbers for, yeah, so for UB it's 0. So I have MA, so if UB is 0, actually this simplifies to this. Right? Just to show you how it would roughly look like as well. Yeah, so this is sometimes called the fractional mass. So how much does MA as a fraction of the total mass? Okay, so this is a combination that will appear a lot in sort of these collision problems. So just to show you, it appears here as well. But now we can plug that in. So I have 1,000 kilogram, 10,000 kilograms, 10,000 kilograms plus 10,000. Okay. And UA, I need to convert that. So I'll show you how to do the conversion as well. So since this is a simple problem, I'll deal with the conversion as well. What I usually do, you use a lot of different methods. I know you've done many unit conversion in other classes, science classes already, but I'll show you a quick way to do it. First, miles per hour, I'll write it as a fraction. Miles per hour. Okay, then I ask myself, what do I want to convert it to? Well, standard SI units, right? The base SI units, which is meters and seconds. So 1 meters per second. So I ask how many miles is in 1 meter. So you need to look that up. So that's roughly 1,600 meters. So that's 1 mile. Okay. So I basically treat this as 55 times 1 miles, right? So 55 times 1 miles, that's 55 miles, right? Divide by 1 hour. So that's what's going on over here. 1 mile equals to that. So all I have to do is, right, times, yeah, let's not write the times, not to confuse things. Yeah, I'll write it here. But 1 mile is 1,600 meters. And I wanted to convert to seconds. So how many seconds is in an hour? So 1 hour is 60 minutes, right? So that's 60 times 1 minute, right? So if that's 60 times 1 minute, so that's 60 minutes, but 1 minute is 60 seconds. So it's 60 times 60, so 3,600 seconds, like that, okay? Or you just remember that fact, 1 hour has 3,600 seconds, okay? So 1 hour has 3,600 seconds. Notice my units is done, okay? There's no need to multiply and divide. It's I don't know, people use very complicated ways. If it works for you, that's fine. But this is a quick trick that is very nice. I've used it here, I've used it here. Basically just ask what is each and then treat it as multiplication. You don't even need to do this step. So just think of this as 60 minutes, right? But 1 minute is 60 seconds, right? So you can just do that. So this is what I'm doing. 1 hour is this. 1 mile is this. This is equal, okay? There is it's an exact equality, okay? So what that means is if you put a brackets over here, it's just 55 times that, divide by that, okay? And that's meter per second, and you're done, okay? So I think I did this earlier. You can double check my math. It's just, I think it's 24 point something, but let's just work with 24 meters per second for two significant figures. Okay, yeah, you can double check that. So over here, we'll plug in 24. Okay. And this is 10,000 over 2,000. So that's really just 1/2, right? So that's 12. So that's 12 meters per second. Okay, so I find the velocity over there. If you want to convert it back to miles per hour, you can do that. You can do the whole thing in reverse. I'll show you as well. But the quick way is, you see that the velocity basically halved, right? From 24 to 12. So in miles per hour, it's also going to be halved. So it's going to be 27.5, I think. Yeah, 27.5 miles per hour. Okay, so it gives you a good sense of how fast that is moving. If you drive a lot, you get a good sense there. But just to show you the conversion one more time, since it's a relatively simple problem, I write it in meters per second. So write these in a fraction, and then ask how many meter. So 1 meter is how many miles. Okay, so how do I do that? Well, I know. So if you looked up 1 mile is 1,600 meters. Now divide both sides by 1,600. So 1 mile divided by 1,600, right, equals meters. So I can put a 1 over here once you divided it. So 1 meter is 1/1600 of a mile. Okay, so you do that times 1/1600 of a mile. Okay, and how many seconds is in an hour? So 1 hour equals 3600 seconds. So 1 second equals 1/3600 hour, right? So if I flip both sides, so 1/second is, do the reciprocal of that much hour. Okay, so this is 1/second. So I have 3600 1/hour. And now you see, you can just do this, divide by this times this, and you will get, you should get 27. You can double check this, around 27.5 miles per hour. Okay. All right, so showed you some units conversion tricks. So if you showed you some algebra manipulation tricks, and also more importantly, the inelastic collision example in 1 dimension. Okay, so this is all momentum is. You see, momentum is a useful concept. Once you understand momentum is conserved, it's useful in just looking at how collision works. And the final thing to look is what can we do this in 2 dimensions? And really, you will see that 2 dimension, just like projectile motion, it's nothing. It's exactly the same thing to deal with. It's just matching up initial and final. Because the only thing you need to know is x and y act independently. So it's just 1-dimensional problems on steroids, not even on steroids, just double it. Okay, we'll see an example. Back to the pool table with a billiard ball, but this time things are colliding at an angle.